Hello and welcome to our next lecture on cyclic codes. Let's start with a brief outline of today's talk. We will revisit the concepts of cyclic codes, followed by the generator polynomial and the syndrome polynomial. Then we will go on to study some of the examples of good cyclic codes, the fire code, the Golay code, CRC codes, which are redundancy check codes. And finally, we will see why cyclic codes are so popular, because they are very so to say friendly in terms of circuit implementation. Then we will talk about the Meggitt decoder. Let us quickly start with a quick recap. We have already studied the basics of cyclic codes, the generator polynomial, syndrome polynomial, and finally the matrix representation, because cyclic codes form a subclass of linear block codes. So, very quickly, a code C is cyclic when C is a linear code and any cyclic shift of a code word also results in a valid cyclic code word. So, cyclic codes are a subclass of linear block codes. We have studied all of that. We also saw that it is possible to have one generator polynomial Gx, which can generate all the other code word polynomials. Before that, we established a one-to-one link between a polynomial and a code word. What we also observed is that Gx is necessarily a factor of x raised to the power n minus 1, where n is the code block length. So, these are the three properties that we actually observed about cyclic codes, that this Gx is a unique monic polynomial, and the multiplication of Gx by any arbitrary polynomial of degree k minus 1 or less results in a valid code word. So, we now look at how we use g of x to generate a code word polynomial c of x. It is simply the product of an information polynomial I of x, degree k minus 1 or less, multiplied with g of x, the generator polynomial. We have already established a one-to-one correspondence between a vector and a polynomial. Therefore, an error vector can equivalently be represented by an error polynomial e of x. So, what we receive is nu x equal to c x plus e x, where e x is the error polynomial. We now go on to defining a syndrome polynomial s of x. What we do is s of x is nothing but the remainder that you get when you get this nu of x divided by g of x, and therefore, we can easily see that it is nothing but the remainder what you get when you divide e of x by g of x, right. We also studied the matrix representation, simply because the cyclic codes form a subclass of linear block codes. So, we can see a very symmetric kind of representation of G. So, what are the rows of G? Each row of G represents a valid code word, but here we have the first row as G0, G1 up to GR, right, and then followed by all zeros. The next row, which is again a cyclic shift, hence another valid code word, it is nothing but G0, G1 shifted up to GR, and then remainder are padded with zeros, so and so forth till k shifts, and we have finally the kth row as G0 zeros preceding G0 up to GR. So, this is a very interesting structure of a generator matrix for a cyclic code. So, if you want to find out the cyclic codes, it is just a matter of factorizing x raised to the power n minus 1. We quickly look at an example. If you are interested in finding out all possible ternary codes, what does that mean? A ternary code are codes with coefficients over GF3, and the block length is specified as 4. Then we just factorize x raised to the power 4 minus 1 over GF3, and we get these three factors. But please note, any factor of x raised by n minus 1 is a valid candidate for a generator polynomial. So, clearly we have x minus 1, and of course, we have to start with a trivial 1 as a factor. 1 is a factor of all of those x raised by n minus 1. Then we have x minus 1, x plus 1 as written here, x squared plus 1 also given here. But then the product of first two terms is also a valid factor and hence a valid generator polynomial. This gives us as x squared minus 1 as a valid generator polynomial. Then we take number 2 and number 3, multiply them out, we get another, and 1 and 3, and I can get another one, and multiply all of them together, which leads to x raised to the power 4 minus 1, which is a factor of itself, and hence these are. So, we have actually a total of 8 factors. Some of them are trivial, but they are all technically speaking generator polynomials, which will lead ternary codes, ternary cyclic codes over GF3 of block length n is equal to 4.
Excuse me, sir?
Yes.
Sir, x to the power 4 minus 1, it is defined over GF3. So, it shouldn't be x to the power 4 plus 3 or plus 2, it is modulo operation. So, how can I factorize it?
Okay. So, the question being asked is about the factorization of x raised to the power 4 minus 1 over GF3. So, please note that any x raised to the n minus 1 over any field can first be expressed as x minus 1 into x raised to the power n minus 1 plus x raised to the n minus 2 plus so and so forth up to x plus 1. This is an identity. So, the first term is fixed, there is no doubt about this one. This is true for any field. Now, we go further and we see that we are working over GF3. So, we focus our attention on this second term x cubed plus x squared plus x plus 1. Now, we try to see whether there is a linear factor here or not, and we substitute. So, x plus 1, now 1 plus 2 is equal to 0 in GF3. So, this x plus 1 is also equal to x minus 2. So, this second term is x minus 2. So, we have to substitute 2 here at x and see whether you get a 0, and if you substitute 2 here, you can check out that yes, x is equal to 2 is a factor here, and consequently x plus 1 leads to be one of the factors of x raised to the 4 minus 1. Now, we divide this x cubed plus x squared plus x plus 1 by x plus 1, and I can get this factor out. So, we factorize this second term into x plus 1 times x squared plus 1. So, it works out, and you can expand this out to get that this is the second term. So, it is a straightforward factorization of x raised to the 4 minus 1 over GF3. So, all of these 8 factors, some are trivial, some are not, are capable of generating a cyclic code each. Please note, we have used the fact that minus 1 is plus 2 because 1 plus 2 is equal to 0 over GF3, and we have listed out all of these 8 generator polynomials in this table. This one contains first 4 and then the next table will contain the other one. So, if you look at Gx is equal to 1, well, it is a trivial n is equal to k is equal to 4. So, this is not really going to give me any error correction, and it is I4, it consists of all the possible code words, all the possible vectors here, and so there is really no minimum distance really useful for us. Now, if you look at Gx equal to x minus 1, right. So, we are looking at the first factor x minus 1 here. So, if you look at that, then you can get the degree of g of x is n minus k. N minus k is 1, n is equal to 4, consequently k is equal to 3, and therefore, you can get a 3 cross 4 matrix as follows. Please note, since we are working over GF3, you can either write minus 1 or substitute by 2. So, this could as well be written as the first row as 2 1 0 0 0 2 1 0 0 0 2 1 as a valid generator matrix over GF3, and the elements of this generator matrix are coefficients taken from GF3. Similarly, x plus 1 is different, and x square plus 1, again you have n minus k is equal to 2, n is equal to 4, consequently k is equal to 2, and therefore, we have a parallel definition for a G here. We look at the remainder 4 factors and we can write it out as follows. So, if you see, we have been able to get 8 distinct generator polynomials and their equivalent generator matrices from here. Now, let us look at the notion of a parity check polynomial. Please remember, we had the notion of a parity check matrix for linear block codes. We are working in a subclass, and therefore, it is possible to find a parity check polynomials. So, we start with a question: do we really have a parity check polynomial corresponding to a generator polynomial g of x? So, we already know that g of x is a factor of x raised by n minus 1, where n is the block length. So, we can always write x raised by n minus 1 as some polynomial h of x into g of x, because g of x is a factor. Now, we observe that g of x is a monic polynomial by definition. Consequently, h of x has to be monic, because the left hand side is also monic. Monic, remember, means leading coefficient is unity. Now, degree of g of x is n minus k. So, a little bit of observation will tell you that the degree of h of x must be k, so that their product leads to x raised by n as the highest power of x. So, now what we do is we start off with a cyclic code C in Rn with the generator polynomial g of x, and we are denoting f x set of all possible polynomials divided by this f x, which is the prime polynomial, by Rn, right. And here you have h x into g x is equal to x raised by n minus 1, but in Rn, so when you take modulo x raised by n minus 1, you get it as 0. So, you have this c of x, which is a valid code word polynomial, and if you multiply with h of x, you get ax into g of x. That is how you generate c of x times h of x, right, in Rn. So, modulo x raised by n minus 1, but here we will get this equal to 0. So, consequently, h of x behaves like a parity check polynomial. What does it mean? Take any received vector, and if it is a valid code word polynomial, then you multiply it with h of x and take modulo x raised by n minus 1. If you get a 0, you can be rest assured that it is a valid code word polynomial. Therefore, it behaves like a parity check polynomial. So, valid code words when multiplied with h of x gives a 0, whereas if it is not, then you have some error. So, error detection is extremely easy with this. We will explore this concept shortly. Now, since we had defined a parity check polynomial, we also have a parity check matrix definition. So, it is very easy to define the matrix once you have the parity check polynomial. Please note the sequence of steps. We have x raised by n minus 1, and x raised by n minus 1 can be factorized to give you h of x and g of x, and then h of x, the coefficients can easily be written in this form. So, if you consider little bit more graphically, then you have, if you look at your slide. So, we have this x raised to the power n minus 1, and the first step is you factorize it into h of x into g of x. Okay. Now, this leads to your coefficients h 0 plus h 1 x plus h 2 x squared plus h k x k, and this g itself would lead to your coefficients sum g 0 plus g 1 x plus now immediately you can take these coefficients and write out your H matrix as h k, h k minus 1, so and so forth till h 0, 0, 0, 0, 0, and similarly 0, h k minus 1, h 0, and then you have this h k up to h 0. And similarly, you have a G matrix which you can write G 0, G 1 up to G n minus k 0, 0, and then a right shift So, the point is your starting point is x raised to the power n minus 1, for which once you know n and you know the Galois field, you are ready to factorize. Once you factorize, you get a great deal because you get g x and you get h of x free. But please remember, h of x is also a factor. So, it is another generator polynomial, and for this g x serves as the parity check polynomial. So, it is kind of a dual here, and once you get these coefficients, you can immediately write out h and g. So, it is a very easy way to get your generator matrix and parity check matrix in the case of a cyclic code, and that is why we spent enough time learning how to factorize over any arbitrary Galois field. So, we come back to our slides, and now having developed this notion of cyclic codes, let us look at some examples here. We start off with a very interesting example of a fire code. Now, one of the very good selling features of cyclic codes is the burst error correction. So, a fire code is a cyclic burst error correcting code over GFQ with the generator polynomial given as Gx is equal to x raised to the power 2t minus 1 minus 1 px. What is a px? Where px is a prime polynomial over GFQ whose degree m is not smaller than t, and px does not divide x raised to the power 2t minus 1 minus 1. So, this is relative prime to p of x. The block length of fire code is the smallest integer n such that gx divides x raised to the power n minus 1. Okay. So, you have to construct this fire code. This is a mechanism how to construct it. But what is the beauty is a fire code can correct all burst errors of length t or less. So, a burst of error is of length t means that the first and the tth error bits are definitely in error, and the remainder may or may not be in error. So, if you again look at a description here, and we now define burst errors. Suppose I have a bit stream. A long enough bit stream. We take a sequence of bits, and if this is t, then this is a burst of error if the first one and the last one are definitely in errors, and intermediate bits may or may not be in error. But this is defined as a burst error of length t. So, all of them can be in error. So, your code should be able to correct that or detect that if it is designed to do so, or maybe the alternate bits are in error, but the stretch is over t, and necessarily the first one and the last one must be in error. This is how we define a burst of length t. So, we come back to our slides and we continue with our fire code with t is equal to 3 is equal to m and a prime polynomial over GF2 of degree 3 can be written as px is equal to x cubed plus x plus 1. You can check whether it is a prime polynomial. You substitute x equal to 1, you do not get a 0, you substitute x is equal to 0, you do not get a 0. So, there are no linear factors of the type x and x minus 1, and then you can verify that this is indeed a prime polynomial. Okay. Now, in our construction in the previous one, x is what 2t minus 1 minus 1, we have already figured out what is this px is. Px is x cubed plus x plus 1. Now, 2t minus 1, right. So, we would like to correct burst up to length 3. So, 3 to the 6 minus 1 5. So, x is for 5 minus 1 into p of x is written as this. So, this is immediately our generator polynomial for the given fire code. Now, this generator polynomial should be able to correct bursts up to length 3. G of x has degree n minus k is equal to 8. The block length is the smallest integer n such that g of x divides x raised by n minus 1, because it needs to be a cyclic code. So, we try, make a few attempts, and we get n is equal to 35. So, n minus k is 8, n is 35, consequently k is 27. So, we find our fire code of size 35 comma 27 with the generator polynomial given as follows. Now, you can check that this code rate for this fire code is 0.77, and it is more efficient than another cyclic code which has a code rate of 0.6, for example. So, fire codes are pretty efficient, and as we increase t, their efficiency tends to 1. So, we will get better and better fire code in terms of the code rate if you have t, which is the number of burst errors it can correct, larger. Now, we look at another example, the Golay code. We start off with refreshing our definition of perfect codes. If you recall, for perfect codes we had this condition. So, we wanted the equality for the Hamming bound, n is the block length, q is the Galois field GFQ, and n is block length, t is the number of errors it can correct. So, if you try out with different integer values of m, n, t and q, and since we are looking at binary, q is equal to 2, we would get n equal to 23, k is equal to 12, m is equal to 2 raised by 12 and t is equal to 3, satisfying this condition. So, maybe there is a possibility that n is equal to 23, k is equal to 12. So, 23 comma 12 code exists. So, Golay was the first one to find this, and 23,12 perfect code exists and is called the binary Golay code. Now, we will explore this perfect code as a cyclic code. Okay. So, the first step is the moment I get a hang on n is equal to 23, I quickly write x raised to the power 23 minus 1 and try to factorize it. Where? Over GF2, because it is a binary code. So, let us try to factorize this x raised to the power 23 minus 1, and with a little bit of effort you can write out these factors. So, immediately we have this as a possible generator polynomial, another possible generator polynomial, yet another possible generator polynomial. Well, this one is trivial and these two are of interest. So, n minus k here is 11. So, if you go back, we should be able to get n minus k as 11 here. So, indeed we have hope to get a perfect cyclic code, which is the binary Golay code. So, please note that for our non-trivial scenarios, g1 x is the first polynomial and g2x is the second polynomial. Both are the generator polynomials of the binary Golay code 23,12. So, we start with this any one g of x. So, degree is 11, k is 12. So, we have found out a cyclic code which is also a perfect cyclic code, right. Now, in order to prove that it is a perfect code, well, we should also show that the minimum distance is 7. Why? Because t, if you see in our previous slide, we wanted t equal to 3. It should be able to correct 3 errors, and we have got n23, k12, but d needs to be, the t needs to be shown equal to 3. So, one way is to write out the parity check matrix and show that no 6 columns are linearly independent. For this, you have to employ a simple computer program, and you can prove that. The code rate is 0.52, and this is indeed a triple error correcting code. But this relatively small block length of this perfect code practically makes it not so practical for real life operations. Code rate is also pretty poor. So, even though it is a perfect code, code rate wise it is almost 50% of the bits are overhead bits. We also have a ternary Golay code. So, if you have x raised by 11 minus 1 and you try to factorize, you get these two factors, n minus k is 5 and k gives k equal to 6. So, we have an 11,6 ternary cyclic code, which is the ternary Golay code. Okay. The minimum distance of this code is 5. Now, let us look at another class of codes which are called the cyclic redundancy check codes, also briefly called as CRC codes. Very practical, very useful, touches our lives on a day-to-day basis. Okay. This employs the property that cyclic codes can detect errors very easily. So, these are check codes, these detect, they are not in the business of correcting the codes. Okay. So, we can have a k bit block of bits, and the n comma k CRC encoder generates n minus k bit long frame check sequence. So, you have the first k bits as the information bits, and then n minus k, the overhead bits, are the frame check sequence bits. And please note, as we have discussed before, what we received in this case, suppose v of x is nothing but what you send t of x plus an error e of x. So, e of x is the error polynomial, and the way to find out is we divide with using the generator polynomial p of x, but what we get is t of x is perfectly divisible by p of x. We have done this before, leading us to have only e of x by p of x. Now we can design a generator polynomial smartly that it catches lot of errors. Okay? In fact, if there are even number of terms in p of x, then odd number of terms in e of x can be caught, and so forth. So the polynomial p of x is called the generator polynomial for the CRC codes, and CRC codes are also generally known as polynomial codes. Some of the popular CRC codes have entered into international standards, and here we have listed 4 popular CRC codes. Both CRC 16 and CRC CCITT are popular codes for 8-bit characters, and for example 16-bit FCS can catch all single and double errors and all errors with odd number of bits, all burst errors of length 16 or less. So they are very effective in catching burst errors, and so forth. I mean, this is just the properties of these polynomials, how they divide and what error patterns they can catch. CRC 32 is a part of the STS, the synchronous transmission standards. So the point is, these CRC codes, which are the subclass of cyclic codes, are very practical and very powerful in correcting burst errors. Well, they can detect definitely, and some of them can correct burst errors. Now we come to a very important selling feature of cyclic codes, which is that they are very amenable to circuit implementation. Okay. So shift registers can be used very easily to encode and decode cyclic codes. Okay. So what is encoding and decoding of cyclic codes? Well, we already have a polynomial representation. All we have to know is how to represent polynomials and put them in shift registers, and then how do we multiply, which actually comes from the FIR circuit theory. So the shift property of the shift registers can easily convert one code word into next, simply because shifting, right shift, cyclic shift of a valid code word is another valid code word. So cyclic shifts are very easily implemented in circuits, and therefore cyclic codes are very comfortably represented using shift registers. So we will focus on implementations for codes over GF to raised by m. So you can have binary and even non-binary representations. So beside the shift register part, we sometimes require, for a non-binary case, a multiplication by a scalar, addition and multiply. So addition is nothing but a binary addition, and multiplication is nothing but an AND gate. So circuit implementation is really the key to fast, cheap, efficient implementation of large cyclic codes. So here are some of the tools that we use, the circuit hardware tools. So you have the end stage shift register, we have a scalar multiplier, we have a simple adder, and a multiplication of 2 bits, for example. So we have all of these very fast, cheap hardware available in today's technology, and therefore cyclic codes are exceedingly important. So we take an example of how GF2 can be used to represent GF2 raised by m. For example, if you have to represent GF8, so cyclic code, non-binary cyclic code over GF8, then the elements are simply represented and in their binary form. So these are the 8 elements of G of 8, but they are easily represented in binary. So for example, if you have to represent 101, which is nothing but a polynomial x squared plus 1. Why? Because coefficients of x square is 1, coefficient of x is 0 missing. So, x is missing and coefficient of x raised to the power 0 1 is here. So, if I substitute 1 0 1 here, then this represents x squared plus 1. So, I can represent any polynomial using the coefficients in a shift register. Now, the other thing that is required in circuit implementation of cyclic codes is the product of two polynomials. So far, we are very comfortably representing a polynomial as a vector and vector as a polynomial. There is a one-to-one correspondence. Now, suppose we want to multiply two polynomials using circuits. How do we do it? So, my candidate polynomials are ax squared plus bx plus c multiplied by, for example, x squared plus x, and then we have to take it modulo some p of x. So, you can multiply it out and you can get these coefficients, and if you simplify it, you can write it as follows. And if I were to implement this using a circuit, well, so I will take a, b and c as coefficients here, and I can always make an observation here and say, okay, let us say the first, this should be my answer. How do I work it? The answer should have a coefficient for x squared, a coefficient for x, and a coefficient for x raised to the power 0. So, let us first focus on the coefficient for x squared. So, it should be a plus b plus c. So, this arrow should have a plus b plus c. So, these are just standard hardware implementation. So, this shift register, tap from here, a tap from here and a tap from here gives the first coefficient. Now, this one should correspond to the coefficient for x, but this should be b plus c. That is very easy to implement. I take a tap from b, c, put an adder and put an arrow here, and same for a plus b. So, I have an a plus b here. So, this simple circuit in an instant multiplies this polynomial. So, it shows how easy and efficient it is to carry out, but we must note that our understanding is that this is the coefficient for x square, this is the coefficient for x, this is the coefficient for x raised to the power 0, same with here. So, if you have to multiply two polynomials in general, one of them is your generator polynomial and the other one is the information polynomial, to get the code word polynomial, and now we are really in business, because this is exactly how circuit implementation for cyclic codes must work. So, b of x is nothing but ax into g of x, and you multiply it out and you get these coefficients, and then you can quickly work together to put any a of x comes in, we load it into your shift register. So, this is the incoming vector which is represented as a polynomial, or the vectors, the elements are loaded here. I already have the coefficients, quickly they multiply and instantaneously you get a bx at the speed at which your circuit works. So, you load in your information word, you get the symbol out. So, it is really a real time operation. The other part of good cyclic code is the division part. We need to divide to carry out these checks. CRC does that. All other cyclic code error detection routinely involves dividing by g of x or some polynomial. So, division process can also be expressed as a pair of recursive equations. So, let q x and r x be the quotient polynomial and remainder polynomial of the rth recursion step, with the initial condition that q x is 0 and r x is a x. So, you can write out these two recursive steps by dividing with respect to g of x, and by forming these recursions you can always get the answer. So, the circuit implementation of this division by g of x is written again like this, again very easy to implement in hardware. So, if you are suppose given the task to find out a shift register based implementation by dividing by this specific generator polynomial, then here is a circuit which will do division by g of x. We finally come to the flow chart of how we do the decoding using a Meggitt decoder for cyclic code. So, first what you do is take the received word and store it in a buffer. Buffer of what? It is nothing but a shift register. Now, we have a very efficient divide by g of x operation. So, we subject it to the divide by g of x operation. Then the remainder in the shift register is compared with all the possible pre-computed syndromes. What is remainder in the shift register is what you divide and get after division by g of x. If it is all zeros, then you have correctly decoded, and it means that no error had happened. But if it is non-zero, then you have to compare. Once again, comparison in hardware is extremely easy. So, you have got very fast comparators available. So, this is again very easy and efficient to do it in hardware. Now, once you compare and identify a syndrome, it corresponds to a correctable error pattern. So, we have a lookup table again in hardware. So, once a syndrome match is found, the error is subtracted out from the received word, all in hardware, and then the corrected version of the received word is passed on to the next stage for processing. So, if you want to represent the Meggitt decoder by a flow chart, you have a received word. First step is divide by g of x operation. We have looked at some examples. You compare it with all the test syndromes and you get an error word. Hopefully, it is in your list, and what you do is take that error word here and then subtract out the error word and you get the corrected word. So, this each and every step here is easily doable in hardware. Therefore, cyclic codes are so attractive because they are very easily implemented in hardware. With that, we come to the end of this lecture. Let us summarize what we have done. So, we started off with the generator polynomial, and with that we also found out the syndrome polynomial. Then we looked at some examples of fire code, very strong burst error correcting code. We looked at the perfect code, the Golay binary code, the Golay ternary code. Then we looked at cyclic redundancy check CRC codes, very efficient in detecting errors, burst errors. And then finally, we looked at how to implement the cyclic codes using circuits. We also looked at the flow chart of the Meggitt decoder. With that, we come to an end of this lecture.